The next speaker will be Aurélio, who will speak about sufficient conditions for unbounded superradiance in black hole spacetime sorted by nonlinear electrodynamics.
So thank you, João, for the nice introduction. So as I said, my name is Aurélio, and today I'm going to talk about this. What? 1 minute, please. Alright, sorry guys. So I'm a temporary professor here at the UFPA and also a postdoctoral research in the graduate program in physics. And today I'm going to talk about this subject, which is a paper that we published this year in collaboration with Luis Leite and Professor Crispino. So I'd like to start with the motivation for this work. Well, we all know that black holes are one of the most interesting predictions of general relativity. And however, GI also predicts that these objects, they have a common feature, which is the existence of a curvature singularity at their core. So our first main motivation is an attempt to go beyond the paradigm of singular black holes, that is those black holes that have this curvature singularity where the no laws of physics break down. And to go beyond it, there are several possible roads. One of them is modify the Einstein field equation. You can change, for instance, the geometric sector, search for alternative theories of gravity. But you can also, of course, try to go to a quantum theory of gravity, which so far we have not obtained a completed one. But there is a more simple road, which is a road where instead of trying to modify the geometric sector of general relativity, we try to modify the source of the field equations. We modify the energy momentum tensor using alternative sources. Among all possible alternative sources that we can use to obtain regular black holes, that is, black holes without curvature singularities, there is one of them which is nonlinear electrodynamics. And by now, most of you are already familiar with the main ideas of nonlinear electrodynamics, thanks to the short course of Buchlik. So I'm not going to give too much details about what is nonlinear electrodynamics. So what you guys have to have in mind is that essentially this is a theory which comes to the 30s, and it basically was an attempt to generalize Maxwell's electrodynamics in the strong field relation, but nowadays and throughout the years it passed for several breakthroughs, and nowadays we use nonlinear electrodynamics especially to obtain regular black holes, which is a topic that has been widely studied these years. So the main idea is basically the following. In 1998, Aurélio and Alberto Garcia obtaining that it is possible to derive regular black holes, electrically charged black holes, without curvature singularities by minimally coupling nonlinear electrodynamics and general relativity. So the main idea of them was basically to replace the energy momentum tensor associated with the Maxwell theory for energy momentum tensor associated with nonlinear electrodynamics, given by this expression here, but not exactly the expression they use in an alternative framework, but the idea, the framework is essentially change the energy momentum tensor by one associated with nonlinear electrodynamics. So what I want to do is try to study not only the physics behind the regular black holes, but also try to understand, try to unveil signatures of nonlinear electrodynamics in black hole physics. And this can be accomplished in several different ways. For instance, we know that in nonlinear electrodynamics, photons follow new geodesics of an effective geometry, which is given by this expression here, where G bar are associated with the effective geometry, where in G without the bar with the standard metric. So basically, the idea is that photons in nonlinear electrodynamics propagate along the new geodesics of an effective light cone, and you are also kind of familiar with these ideas due to the annual seminar yesterday. here, which is also work that we have done together. But here, I want to explore a new perspective, a different perspective actually, where we try to review signatures of linear electrodynamics, not looking to the motional forms, but now looking actually to how charge and mass and scalar fields interact with black holes associated with linear electrodynamics, especially because in this case we have this term associated here with the electrostatic potential that depends on the space-time. So what is the idea behind it? So the ASP is considering, first of all, the highest motion black hole, which is a spherically symmetrical black hole described only by its mass and charge. So the idea is kind of very simple. Imagine that we have a scalar field coming to infinity towards the black hole. When the scalar field is going to the black hole, and we call that this scalar field has mass and charge, the scalar field will interact with a potential barrier, and it will be partially transmitted into the black hole and partially reflect back to infinity. And the fun thing about it is that there is a possibility where the scalar field is reflected by the black, is scattered by the black hole with more energy than it originally had. In this case, the scalar field is still energy for the black hole in the process that we call by superradiance. And this is the superradiance scattering, which was discussed by Carl today. So, okay, so we can have superradiance in space-time, in spherically symmetric space-times, considering massive and charged scalar fields due to the Coulomb interaction. So let's put the highest motion black hole aside, and what you can do with this scalar field is compute its total absorption cross-section, which is basically the total amount of the flux that goes into the black hole, the ratio between this and the incident flux. So this quoted here, the total absorption cross-section basically computes how much of this wave is absorbed by, of the scalar field is absorbed by the black hole. In the case of the highest motion black hole, there is three possibilities for the total absorption cross-section. We have unbounded absorption, so that means the total absorption cross-section diverges in the low frequency regime. We have bounded absorption. In this case, the total absorption cross-section is finite in the low frequency regime, but it doesn't but we do not have the superradiant scattering. And we have the third possibility where the total absorption cross-section is bounded, but we have superradiant scattering. This is for the highest motion case, which is a black hole associated with linear electrodynamics with Maxwell's theory. So now let's replace. So of course you can put this on the map where we can see the bounded absorption, the bounded superradiance. But this is for the highest motion case. So let's change the highest motion black hole for a black hole associated with linear electrodynamics, which is that black hole that I've shown to you before. In this case, instead of this kind of behavior for the total absorption cross-section, we now have this one over here. The bounded absorption region is replaced by what we have called by unbounded superradiance. So in this case, the total absorption cross-section diverges negatively and is unbounded from the low. So the wave is extracting an infinite amount of energy from the black hole. So the question is, what are the sufficient conditions to treat unbounded superradiance in natural black hole space-times? Because we have obtained these results for the Ayón-Beat-Garcia regular black hole, which was the first regular black hole, electrically charged regular black hole in the literature. But we want to go beyond that. We want to explore the scenario where we have the unbounded superradiance in what are the sufficient conditions to have this in arbitrary space-time associated with linear electrodynamics. So let's move on to the setup. So, well, we have a spherically symmetric space-time where f of r is a metric function that will be written in terms of the quantity associated with linear electrodynamics. The scalar field satisfies the equation 2, and the effective potential is given by this expression here, where mu is the mass of the field, omega is the frequency, q is the charge of the field, and this term is really important because it's the electrostatic potential of the black hole, right? So The boundary conditions I have already discussed it with you, so we have a wave impinging onto the black hole, which is partially transmitted into the black hole, partially reflected back to infinity. These terms are all defined here. So the important thing is that here is that you can decompose a scalar field as a sum of partial waves contributions. In such a way, the total absorption cross-section can be written as given by this expression here. And when we have a super radiant scattering, and of course, let me just point out that the critical frequency is given by this term here. So when we have a super radiant scattering, omega is less than this critical omega, and the total absorption cross-section is negative. So during the super radiant scattering, this quantity here is negative. And this is the transmission coefficient. So to discuss what are the sufficient conditions, we need first to discuss in what scenarios we have unbounded absorption. And we have unbounded absorption. To see in what scenarios we have this, we need to define a new potential function given by equation 7. And we can read the unbounded region for the equation 8. So the idea is basically the following. So if you try to compute the critical value of charge that satisfy this equation, where R max is the maximum of this potential, we will see that for Q less than critical Q, where of course Q is the charge of the black hole, we will see that the Newtonian attraction is greater than the Coulombian repulsion. And this means that the Coulombian repulsion cannot counterbalance the Newtonian attraction, and if this condition is true, then we have unbounded absorption. But of course, if you have unbounded absorption, you not necessarily have super radiant scattering. So the second condition is the condition for super radiant scattering, and this condition is satisfied by equation 10. So if omega is less than critical omega, we have the super radiant scattering, the total absorption cross-section is negative. So now we have the two conditions. The first one leads to unbounded absorption, and the second one to super radiant modes. But super radiant modes do not necessarily exist in the same region where we have unbounded absorption. And to ensure that this is true, we define this quantity here, and we can actually show that if this quantity here, defined by this equation, is greater than the unit, in other words, if the electrostatic potential of the module and the event horizon is greater than the electrostatic potential of the Heisenberg space-time, then we can make unbounded super radiant modes feasible. And this means that we can have super radiant modes in these situations where we have unbounded absorption and super radiant scattering. So these are the three sufficient conditions to have unbounded super radiance in non-associated space-times. So to conclude, the takeaway message of this talk is basically the following one. What are the sufficient conditions to trigger unbounded super radiance in non-associated black hole space-time? So we have three sufficient conditions. The first one is associated to unbounded absorption, to the total absorption cross-section being unbounded. The second one guarantees that we have a super radiant scattering, and the third one makes feasible the existence of this super radiant mode in the situation where we have unbounded absorption. So, as future perspectives and also ongoing research, of course, you can explore this in other astrophysical objects, such as wormholes. But we are trying to answer this question here: does unbounded super radiance necessarily imply in super radiant stability? Because these are two different phenomena that are actually connected, but you need to prove it formally. So that's all. Thank you all. Any questions or comments?
We have time for a couple of questions.
So I was thinking about the case because when you were showing that the graphic I think it was one of the first ones.
Okay, beginning, right?
Yeah, at the beginning. When you were talking about
Alright.
unbounded super radius.
Okay, I'm also radius here.
Yeah. So go to the next one. I think
This one?
no
This.
the next one. Because when you have the unbounded super radius, you have the total absorption cross section going to minus infinity, right?
Yes.
Yeah, and it says something about in this case, it's like you are stealing energy without any limitation, right?
Yes.
But you can say that because you are kind of not considering the backsketch in your geometry, right? Because
Yes.
in reality you will have
Yes.
cannot be really unbounded, right?
Yes. So if I
Yeah.
So yes, if you can see, well, we didn't do that for the Heisenberg for the Aurélio case, but if you consider, for instance, the Heisenberg black hole at the nonlinear level, so we consider the back reaction of the scalar field in the Heisenberg black hole, we can have this kind of effects, but this is not going like forever. It stops sometimes. So I suppose that I'm not sure, but I suppose that if we do like a proper evaluation of the scalar field in this space-time associated with nonlinear dynamics, perhaps the contribution, the back reaction of the scalar field in geometry will be capable to, I don't know, surpass, to stop this, to go indefinitely.
Yeah, because if you consider the evolution of the system, you're probably going to fall into the case where the condition is saturated, right? So
So in the case we can steal all the energy of the black hole, what would be the remnant?
So this is a very good question, because when we say that the wave is stealing energy from the black hole, what is the energy that the wave is stealing from the black hole? Is from its mass or is from its charge? So in this case, there is this coupling occur. The coupling that allows the super-radiant scattering between the electrostatic potential of the black hole and the field of the charge of the scalar field. So I don't know what is going on, what is going to happen for this case, because we didn't try to understand things from this perspective. But for instance, in the Heisenberg case, we do not have this unbounded superradiance, and what we observe is that the mass of the black hole diminish, right? So for the Aurélio case, I do not know if the black hole will diminish to mass tends to zero, something like that. This is something that we actually need to check to see what will occur with the mass and the charge of the ADG regular black hole in this case. This is something that we need to check.
Okay, let's think macro again.